So with that, Feng Xiao.
Goodbye. Hi, everyone. Thanks for coming. I'm Feng Xiao, a zero-year PhD student at the Pennsylvania State University. And there's supposed to be another speaker, but he can't come due to some visa problems. So I just put his picture here and my stand so we can together to give the presentation to you all. Thank you. All right, so today we are going to talk about the new attack. The attack is about, with this attack, a weak adversary is able to hack the brain of the software-defined networks, the SDN controller. Well, here is the difference between the legacy networks and the software-defined networks. The legacy network is always vendor-dependent. It means the network's devices always work independently with predefined functions, and we cannot change it anymore. But in SDN, the whole network is treated as two planes, the control plane, the upper layer, and the data plane. So all network functions are now being placed into the brain of the network, the controller, and the host and switch, this forwarding device, are now placed into the data plane. All right. So this is the difference between the two networks. So, and this new architecture now is widely deployed in production environments with growing communities. On the one hand, the open source organizations like Linux Foundations are supporting a large number of SDN projects like the Open Daylight, Floodlight, Honors, and companies like Huawei, Cisco also release their commercial products and their applications. And on the other hand, the growing community accelerates the replacement of the network infrastructure. For example, the world-leading web-scale providers such as Google, Microsoft, deploying SDN in their data centers. So this is how SDN are used today. So when some people are using it, we people are considered to hack it. When the attacker can successfully break into a software-defined network, just like we connect to the Wi-Fi here, if it is a software-defined network architecture, so he will probably target at the controller, because it is the brain of the network. In this talk, we concluded 3 categories of common attack objectives for attacks on the control planes: the denying of service, data leakage, and network manipulations. And in these tables, some objectives have been achieved by previous researchers, and some are not. And we discovered that these existing attacks, for example, just like the topology poison attacks, are all focus on the service logic of controller, which means these attacks, for example, the topology attack, he will attack the topology discover service in the controller to report false links and let the controller make wrong decisions. To discover these vulnerabilities, you should be a hacker and an SDN expert. You should know the details of the SDN protocol interactions, the relationship among this service logic. But I think most of us are not SDN expert, and we even not so familiar with SDN. But it is widely used. So how? So I'm considering whether I can find a method to hack the software-defined network without learning so much about SDN. And my attack should be powerful. In the best case, it should achieve all the attack objectives in this table, all of them, no matter it is an existing one or a new one. So how to hack the SDN like a hacker? Well, the controllers are software systems, and we both know that the software systems are inherently vulnerable. So it is possible that the controller components contains vulnerabilities. This is cool, because we are hackers and we know how to find these code vulnerabilities, right? However, the data plane and the control plane, as I mentioned, they are decoupled, which means they only communicate with each other with predefined protocol interactions. So this architecture makes us hard to exploit these code vulnerabilities from the data plane where we are always in. So in this talk, we introduce the custom attack, which breaks the border built by the decoupled planes. Unlike previous attacks that focus on attacking the controller service logic, custom attack can be used to attack all kinds of code vulnerabilities in the controller. So how to do it? So let's see how to conquer the difficulty built by the decoupled two planes. The SDN protocols provide some fields to let the switch and network device to custom themselves. Usually, the customer field is subscribed by a specific controller components. For example, if a switch may send a fault notification message to the control plane, and this message will be first collected by a service. We can call it a collecting service, maybe. And the service will send the message to its subscriber, maybe a network monitor component. So this is how the customer field works. So I'm sorry, my hands are a little bit tired. So maybe Jianwei, I will put you on the table. All right, let's move on. So there's a semantic gap built by the customer field. Since the customer field can be totally controlled by the data plane, by the hacker, so any improper treatment may break the security border of the decoupled control plane and the data plane. Let's revisit the notification example. The monitor components does know how to parse the notification message. However, the collecting service, who collected it first, does not. So the collecting service may store the message in the database without any security considerations. If a hacker injects a malicious SQL into the customer fields, the database will in danger. And this is the start of custom attack. And this is only the start. All right. And with the custom attack, we can exploit serious vulnerabilities in the SDN controller to bring several advanced objectives. For example, we can issue arbitrary SDN commands by calling the exposed network management API, or we can read some confidential data via SQL injection or other things. And this is the threat model of the custom attack. First, the hackers don't have to directly access the network of the controller, which is sometimes separated from the data plane, the network devices. And he will not need to access any applications in the controllers. Also, the hacker don't need to hack into the encrypted protocol channels between the control planes and the data planes. What the hacker needs is only to perform legitimate protocol interactions with the control plane. So a malicious host or switch is enough. Just like we can use a mobile phone, you know. However, after attacking a vulnerable components, handling the malicious customer field, we can only introduce limited effect to the network. There are several reasons. First, every single component in the controller runs in separate context. For example, just like an independent thread. So the failure of a single component will not affect the availabilities of others. And second, the critical components are usually specially protected. As a result, it is difficult to abusing these important ones if we cannot attack them directly, attack them with these customer fields. So as a result, if we want to do something big, we need a more complex attack, a multi-stage exploitation to control more resources in the controller. This is the workflow. The lower part is the data plane, where there are network hosts and switches. Normally, they cannot directly access the controller because the two networks are always separated. But they will always be able to interact with the controller using the SDN protocols like the OpenFlow or other things. So we need several stages. The first stage is the toehold stage. This is where we attack the components with customer field. In this step, we will inject our craft payload into the customer field and send them to the control plane via legitimate protocol interactions. After the first exploitations, we can now control we can only control a small number of ASET in the component. To harvest more control plane ASET, we need a harvest stage. We will need to exploit more vulnerabilities in other components with previous controlled ASET. For example, we may able to launch HTTP request in the first stage. So in the second stage, we can leverage this ASET to do more things. We may access the REST API to issue some commands. So after we controlling a large number of ASET, we try to chain them together to achieve our advanced attack goal. And as you can see, instead of merely attacking the components that handling the customer fields, with this attack model, we can now able to exploit all kinds of vulnerabilities to hack more components. Okay, now it's time for us to hack something real. First, I will show you a video demo. In this demo, we attack an open source controller. It is maybe the most popular one, the Honors. And the attack effect is we get a remote shell from the controller. Okay, and the Honors controller is on a remote machine, the 111. And our compromised switch is this machine, the 108. So, and this is the web component of the Honors. We can see that there's no devices in the controller yet. Okay? And we can load our framework to attack the Honors controllers and get a system shell from the controllers. This is our devices connected. Well, as you can see, we successfully get the system shell. Yes. So this is an exploit chain with multi-stage exploitation that works. So how it actually works? Next, I will give you more details about the RCE chain. As shown in the picture, our target is the get diagnostic function, which read and execute a script from the file system. So to abuse this function, we need to control two ASETs, to harvest two ASETs. The first is the script itself. To execute arbitrary commands, we need to inject payloads into the script. However, controlling the script is not enough. We also need to access the REST API that calls the diagnostic function. As I have mentioned, important components are usually specially protected. So the REST API is protected by basic authentication. We need an authentication token for this REST API. Let's check out what ASET we can actually control in our first stage. Well, we found XSS in the web component, as you can see. This vulnerability can be exploited by a customer field. So now we can control the ASETs that expose to the XSS, such as some network configurations, However, we cannot still directly attack our target function. So let's move on the second stage, the harvest stage. First, let's try to handle the basic authentication issues. We found that the authentication token is stored as plain text at a config file. So as long as we can control and read this file, we can get the token. This means that we need to find a new vulnerability that can read some contents. After several days hard work, we find our fourth 0 days in Anonymous. It is an XSE. It can be exploited by a customer field that we control. As a result, we can read the token to solve the auth problem. Now we can try to control the script asset with the fifth 0 day we found in Anonymous. It is a path traversal bug in the unzip function. This function is to handle the zip files uploaded from the web component. Remember that in the first stage, we discover an XSS vulnerability in the web component. Now, we can leverage this XSS to upload a craft zip file and then overwrite arbitrary files with any content we want. So finally, we control the script. This is the complete attack graph for the exploit chain. We use 5 previously unknown vulnerabilities in 3 different stages to construct this remote command execution chain. I'm sorry. So how about the impact of the customer field? We analyzed 5 popular SDN controllers, and there are 54 applications. In total, we identify 18 vulnerabilities and construct 24 exploit chains. And all these exploit chains are involved in 2 or 3 stages. This is the impact of these exploit chains. All these exploit chains we construct can introduce a serious attack effect to the controller. And this table shows all the 0 day we found. As we can see from the last column, every vulnerability can be used to introduce more than one attack effect. And we found that Anonymous has the largest number of vulnerabilities. And I think this is because Anonymous is very easy to use. We can install any components we want with a simple click. By contrast, hacking the open daylight is very difficult. To install or debug a component, we need to spend the whole afternoon, and usually we found nothing. So we can only find 3 bugs in the open daylight. So maybe making your project hard to use can be a great defense. Yes, that's what I are important findings in our research. Okay, that's all. Thanks for listening. Okay, I forgot him.